G'day. Now that we've come to the end of a series on how to graph asymptotes and how to analyse polynomial functions, we're going to examine rational functions once more. Now you might recall that a rational function is a ratio between functions, specifically one polynomial divided by another polynomial. They must be polynomials to be considered a rational function. Now, there are three kinds of rational functions. We divide them into three categories. The first category is where the more powerful function is on the bottom. That is, the degree of this polynomial, the highest power, is greater than the degree of the one on top. The second one, they're matched in power. They've got the same degree. And the third kind, the top function, is the more powerful. It has the higher degree. And I'm going to devote a separate video to each of those three kinds. So the first kind, for example, would include functions like this. 1 over x minus 2. X over x squared plus 3. Or x minus 2 over x squared minus x. Or x squared over x cubed minus x, for example. In all of these, you can see that the degree of the polynomial on the top, here its degree of 0, is less than the degree 1 underneath. Here we have degree 1 and degree 2, degree 1 and degree 2 and degree 2 and degree 3, but always a lesser degree on the top. I might just make there we go. That might be an interesting collection to graph. In fact, I might even add one more. Probably be good if we graphed all of those, in fact. But that's the nature of type 1 graphs. When we analyse them, there are a series of steps that we should engage in. So let me explain those before we get going. Step 1 is to look for horizontal asymptotes. Now, with these particular functions, type 1, the horizontal asymptote is always y equals 0. It's always the x-axis. So we really don't have to query that. Now, if you're in a situation where you need to prove it, then you would take the limit of these. And I trust you remember how to find the limit. I'll deal with one of them. Let's take this one, for example. What we would do is we'd say the limit as x goes to infinity of this expression is something or other. Now, because I don't have room, I'm going to perform the first step here. I would look for the biggest power of x, which was x cubed, and divide everything by it. So I'd have x squared on x cubed on the top, and x cubed on x cubed here, and x on x cubed here. And I would say that was equal to the limit as x went to infinity of, now x squared on x cubed is 1 on x cubed on x cubed is 1, and x on x cubed is 1 on x squared. Now when you go to infinity, any fraction with an x on the bottom will become 0. You can appreciate that 1 over extraordinarily large numbers are very, very tiny fractions. And as the number becomes infinite, the fraction shrinks to 0. So this limit, sorry, I shouldn't have an equals there. This limit is 0 over 1 minus 0, because both these fractions shrink to 0, and this becomes 0 over 1, which is simply 0. So y equals all of that becomes our asymptote. And you could do this with any of these functions. Divide everything by x, divide everything by x squared, multiply this out and divide everything by x squared, divide everything by x squared, and so on. So we've established that. The second thing is we look for vertical asymptotes and notice their nature. Now, in looking for vertical asymptotes, we look in the denominator, and we like it when it's factorised. If it's not, we attempt to factorise it. And this will tell us, in fact, where the graph is. When I'm talking about nature, it may be that one of these factors is squared, in which case I have a double asymptote. That's what I'm talking about, the nature of how the curve's going to behave around a double asymptote. The third thing we look for are intercepts. Intercepts always help us in graphing, and to find intercepts we substitute y equals 0 and x equals 0. Now, in these particular graphs, the type 1 graphs, there's no point substituting y equals 0 for the simple reason that it's an asymptote, which means there's no part of the graph touches that line. So it's absolutely pointless substituting it. We won't find a value. There's no point. But we can substitute x equals 0 to find a y-intercept, and that will certainly help us in our journey. The fourth step is to look for a starting sign, or a starting region, if you like. And here's where we're looking at the sign, the coefficients in front of the numbers, to see whether we're going to start in our graph in this area, section, or this section. So that's our starting region. And the fifth thing is to note any zeros in the numerator, because zeros, now I haven't told you the whole story about this. Although y equals 0 can be an asymptote at each end as you go towards infinity, the fact is that lines can cross asymptotes in the middle. So this is not an entirely true statement, but we do note zeros because they're going to give us a sign change. A sign change. And we're going to go through these 5 steps every time to graph the functions. Now, I've been all over the board here. What have I done so far? I've explained what rational functions are. I've explained about type 1 functions, where we have a smaller polynomial on the top, a lesser power, a lesser degree. And I've talked about the 5 steps of analysis before we start graphing. Now, I'm going to start with simple graphs and build up. The first ones I'm going to start off with are going to be like this, with a constant on the top. So let's have a look at a series of those, and then we'll look at some where we don't have a constant and we can start having sign changes. I think that'll be a good journey. Now we're going to analyse these 4 graphs in fairly quick succession. I of course am going to pause to erase the graph each time, just so that it doesn't get too cluttered up. But that's what we're going to do. Now, first thing to note is they're all type 1 rational functions. They've all got polynomials divided by polynomials, and in every case we've got a lesser degree on the top and a more powerful function on the bottom in the denominator. First thing, the y-intercept, the y-asymptote is the x-axis, the horizontal asymptote. That's the case with all of these. This one, we look at the vertical asymptotes now, and the vertical asymptote will be where x is 2. That's step number 2. Step number 3 was to look for zeros. Now, look for intercepts. When y is 0, there is no answer, because 1 over something can never equal 0, but when x is 0, y is negative 1/2. So we do know that it goes through y is minus 1/2 there. And with the asymptotes here, that confirms that we've got part of the graph down here. By the way, I didn't talk about the nature of this asymptote, that it is a normal asymptote. The only strange one here is this one where we have a double, and we'll deal with that shortly. There are no sign changes because we have constants on the top. So the only question really is, where do we start? And because it's a plus x and a plus y and a plus 1, we're going to start up here. Now, this is a simple hyperbola, and because it's a hyperbola, we're looking for numbers that multiply to make 1. So we have, starting here, we go across 1 and up 1, and we come back 1 and down 1. And I'm relying on the fact that you've seen my previous videos here, otherwise this might seem a little bit confusing to you. And if it is, then I encourage you to go back and see the rest of my series. But that's the graph of this first one. So let's tick it off. Let's now tackle the next one. Now, this particular equation, again, because it's a type 1, has a horizontal asymptote on the x-axis. Its vertical asymptote this time will be where x is minus 1. And its nature is, it's just a normal asymptote. We now look for the intercepts. When x is 0, y will be negative 3. When y is 0, there is no answer. Let's talk regions. Positive, positive, negative. So it's not going to start here, it's going to start here. And this makes sense because of where the intercept is. So we're going to have a graph here. This again is just a simple hyperbola. And there's no change of sign in the numerator. There isn't for any of these. So we've now gone through our steps. We're going to draw it, and since it's a normal hyperbola, we're after two numbers that multiply to make minus 3, starting from this point. 1, 2, 3 times minus 1, or 1 times minus 3. So that confirms the point we've got. And there's our first part of the curve. And because they're both normal asymptotes, then I'll have a corresponding part up here. So starting here, 1, 2, 3 and up 1, or back 1 and up 1, 2, 3, and my other part of the hyperbola. Wow, that's a bit wonky. Ah dear. Gross motor skills not doing well today. There we go. And that's that particular graph. Now things are starting to get a bit more interesting, and I trust you're going to watch to see what happens with this one. Let's have a look. Okay, go through our steps again. This is a lower degree than that, so it's a type 1. So our horizontal asymptote is on the x-axis. Vertical asymptotes, well, we have one at x equals 1. There it is. And we have another one at x equals minus 2 or negative 2. There it is there. So already this is getting a little bit more complicated than the first two. It's even more complicated because in discussing the nature of the asymptotes, this one is a double. I'm going to put a little bit of a red dash down here as well. I'm trying not to get my red pen too blackened by the other. I don't know whether you can make that out, I hope you can. But we're going to consider that a double asymptote. What's the next thing? We look for intercepts. Well, y cannot possibly be 0 because 4 over a number can't be 0. But we can put x equals 0. Minus 1 squared is 1. Times 2 is 2 on the bottom. And 1 times 2 is 2. 2 into 4 goes twice. So y equals 2 is the intercept. Now, that confirms that we're going to have part of the graph up in this section here, bounded by these asymptotes. This need not be a boundary, by the way, but that's coming. Next step is to talk about the region we start in, where we have a positive coefficient of x, positive coefficient of x, positive coefficient of y, and a positive number. So our first part of the curve is going to be here. Now, because this is more complicated than a normal hyperbola, we're not just looking for numbers that multiply to make 4. To find out where it actually exists, you'll have to substitute. But I'm just going to put a curve here. That's in the right region and it's the right shape. But where exactly the points are is up for you to substitute and find out. You might substitute x equals 4, for example, and see the value. Because this is a double asymptote, this part of the curve is reflected in it. And now this makes sense. The curve obviously comes down through here. This doesn't necessarily mean that's the minimum position. It might go through like that and back up. In the next set of questions, we'll talk about when it might actually cross through. And then we have a normal asymptote and a normal asymptote, so we'll have a section of the graph here. So that's a graph of this particular function. And what made it a little bit tricky was having a double asymptote. So far, so good. Let's look at the last one, which is a little bit unusual again. Okay, we're looking at this one now. I should have ticked that one off. We first of all observe that it's type 1, which means our horizontal asymptote will be lying on the x-axis. Now, vertical asymptote, we cannot factorise this in the real number system. If that was a -1, we would have a difference between squares, and we could, but with a +1 we can't. So this is always going to be positive, which means, of course, y is always going to be positive, 3 over a positive number. But we get no asymptotes vertically. Well, that's different. That's interesting. What's the next step? There's no point talking about their nature. There's no point talking about which region, because, except for the fact that y is going to be positive, so our graph is entirely up here, where y is positive. And the last point about changing sign is not an issue because it's always positive. So we need to go ahead and graph it. We don't have much to go on. Oh, intercepts. Y can't be 0 because 3 over a number can't be 0. But if x is 0, y becomes 3 over 1 or 3. There we go. So we do have a position. We do know that out towards infinity, this is an asymptote. And we do know that out towards minus infinity, it's an asymptote on the positive side. So what's the graph to do? Well, it turns out it's got to be continuous because there are no asymptotes. It turns out it does that. What an exciting life that little graph has. But there it is. There, four of the more foundational or simple type 1 rational functions. I'm now going to graph 4 of the more difficult ones, and we'll have a look at those. You're observing already that the key is being able to factorise to be able to find the relevant bits. Notice what's new here. In each of these we actually have a function on the top that is not constant. Now this means that it will change in value which is a bit like, if you're still thinking in terms of constants, it's like the constant changing in size. But more particularly, there are values for which it will be positive and values for which it will be negative. So let's see what effect this has. In the first graph, again, because this has a lesser degree than that, power of 1, power of 2, we know that the horizontal asymptote is on the x-axis. If you're very, very quick, you can see this can be factorised. So we actually have two vertical asymptotes. I didn't mean to put them this close together, but one of them will be on x is 0, and the other one will be where x is minus 1 or negative 1. What are in nature? Well, these are perfectly normal asymptotes. No doubles. We have a surprise waiting for us down here, but there's certainly no double asymptote up here. So we've discussed the nature. What about intercepts? Well, if x is 0, we get minus 1 over 0, because x is 0, which is nonsensical. So there is no, when x is 0, there is no value of the curve, and we can see why. We have an asymptote here anyway. But there is a value of x that makes y 0, and that is x equals 1. And you think, what is that point doing on an asymptote? There's our asymptote. Well, the reason is that something happens when x is 1. You notice that when x is greater than 1, this is positive. So I'll put here positive when x is greater than 1. And it's negative when x is less than 1. That's important to note. So if we go up the positive end of the graph, up here, where x is positive, we get positive coefficients of y and x and x and x. So our graph will start here, like a normal hyperbola. That's what it will do. But what's the effect of having this point here, of having the x minus 1? Well, it's a continuous function here. The only discontinuity is here and here, where the asymptotes are. So this graph actually has to come around and bend down through here. Now, why does it do that? Well, the instant that we move below x equals 1, so the instant we move down into this region of the graph, this number on the top behaves like a negative number. Now, if we had started off without this here, and if I just had a minus 3 or a minus 5 or a minus 1 on the top, we would have looked at positive, positive, positive and a negative and said our graph had to start here. Guess what? From x equals 1 this way, that's exactly what we get, is this part of the graph. And then behaving like normal asymptotes, we have a bit. I didn't plan this. There's a long, thin little loop here. My goodness, it's wobbling everywhere. On a piece of paper, hopefully with fine motor control, your hand will be a bit more steady. And then diagonally across here, we'll get a portion here. So there's something a little bit different. Sorry, I'm trying to make that look like it's getting closer to the asymptote. So there's the graph for this particular function. A little bit different. And we have this crossover point because of that x minus 1. Now you might have guessed it. We're going to have the same issue arise because of these numerators in each case. So let's have a look at the next one. Let's look at the next equation. Again, I'm going to rush a little bit just over this first statement. You know it's a type 1, so there's our horizontal asymptote, and it's a normal one. Where are our vertical asymptotes? My goodness, that can't be factorised in the real number system, so there are no vertical asymptotes. So this looks like one of these ones we had in the previous group of questions. Now we have positive, positive, and if this x is positive, we would expect to be starting our graph up here and have an asymptote coming down like this, which is perfectly reasonable. Let's look at the intercepts. When x is 0, y is 0, so it must cross here. So again, we have it crossing the asymptote. And I think you see that when x is, if you want to put a loop around this, you can say positive when x is greater than 0, negative when x is less than 0. So obviously, how the graph behaves here and how it behaves on this side are different. How does it behave on this side? Well, when x is negative, x squared plus 1 will still be positive, but now x is negative, so a negative over a positive is a negative. It will still come towards the asymptote, but from the negative side. Well, here we have no asymptotes, so it's got to be no vertical asymptotes, so it's got to be a continuous function. It must be asymptotic on the positive side there, asymptotic on the negative side here, and pass through that point. Well, you can see it's got to do something like that. Now, where these points are depends on your calculus and such like. We can just plot some values to find out some key points, but that's the basic shape for this particular graph, so we'll tick it off. Let's look at the next one. Now, this is getting a bit more complicated. We'll see what it's got in store for us. Well, let's start with our third equation. I've circled this to get us started, but on second thoughts, we'll do the whole thing in order. What are our horizontal asymptotes? Well, as with all of these type 1 rational functions, it'll be on the x-axis. Our vertical asymptotes will be at 3 and negative 2. I'll put in the negative 2 first, and then at 3. And if we discuss their nature, you notice that the one at 3 is squared. We have a double asymptote here. So I'm going to use my increasingly black-red pen to just enhance that line a little to remind us that it's a double asymptote. So the graph is going to be reflected in that. Whereabouts would the graph start? Well, positive, 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 and positive. We would expect it to start up in this region. So I'll just put a little curve there to get us started. But we've got a problem. When we start talking about the sign, that's why this is circled, you can see there is a value for which this is 0. So there is a value that y equals 0, and that is when x is negative 1/2. Now, this expression here is positive when x is greater than negative 1/2, and it's negative when x is less than negative 1/2. So as long as we've got large values of x, this will be a positive number, and everything will behave as we would expect with positive, positive, positive. But when x is less than 1/2, it's going to behave like we had a negative graph in the other regions. So it's going to behave, where's negative 1/2? Here it is here. So above here, it's going to behave the way the graph would normally behave. Now, when I was doing this, I didn't take account of the fact we have a double asymptote. So this one will continue up here. And because this is a double asymptote, we expect this to continue down here. And normally it would be in here, and then the last bit would be there. But something's going to happen at x equals minus 1/2, and the graph is going to flip. So it's actually going to come down and pass through there and go down here rather than back up that asymptote. And then, because this is a normal asymptote, both these are normal, we go diagonally across and fill in the other part of the graph. So that was a little bit more unusual. and that's that one taken care of. Notice the double asymptote caused these to match and march up the same asymptote, and at -1/2 we had a changeover occurring. So you can guess we've got a changeover occurring here. We've got two double asymptotes and we've got a negative start, so a few things will happen here. Let's have a look at that. Well, we certainly have an interesting graph for our fourth one. Let's go through the procedure. This is a type 1, so our horizontal asymptote will be on the x-axis. Its vertical asymptotes will be at 3. That's a normal asymptote. At -2, that's a double. And at +1, and that's a double as well. So I'm going to highlight the doubles with red. There we go. So we've looked at the vertical asymptotes and their nature. Now look at our starting point. Well, again, positive, 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 positive. Oh, we've got a minus sign at the top. So I would be expecting our graph will be starting out here. Not on the positive side, but on the negative side. What about the change of sign? Well, when x equals -1, y would equal 0. We've got a problem happening at x equals -1. There it is there. Something is going to switch over. And essentially by now you know that we're going to have a graph either do this or go the other way. So let's finish this off. We know that this will continue down here. This is a normal asymptote, so diagonally across we will have this sort of thing occur. This is a double asymptote, so it will need a bit of the graph on that side to match that one. And it will come down through here. By the way, I didn't check what the y-intercept was. Let's put x equals 0. If x is 0, we get -1 on the top. If x equals 0 here, we get -3 times 2 squared times -1 squared. -1 squared is 1, 2 squared is 4. So -3 times 4 is -12. -1, oh dear, -1 over -12 is +1/12. So this is way off. This would come way down here and zip across at 1/12. 1 over 12 on the y-axis. That's extraordinary, isn't it? Quite a sudden swing across. And then once it goes beyond -1, the graph will flip. And instead of going back up here, it will go down there. And because this is a double asymptote, it's going to be matched by the corresponding part of the graph here, and it will be asymptotic out here as well. So this is a rather unusual one. We have a bend, a loop here, a kind of a zigzag in the middle, and another bend. But I hope you can see how reading the graph helps you analyse what the asymptotes are telling you and what the crossover point is telling you. Everything else is just detail, substituting points and getting more exact parts of the curve. Now, I'm going to look at just one or two more complicated examples. This is a long video, but I want to make sure it's thoroughly covered in the one video. So let's have a quick look. Okay, I've decided on just two more. So let's try and do these quickly. Again, horizontal asymptotes on the x-axis. Vertical asymptotes, we have one at -5 or -5. There it is there. We have one at x equals 0, which, and both these, by the way, are double asymptotes. We have one at +4. You can see that when you're given an equation to graph, your primary algebraic objective is to factorise it and get it into a fully factorised form. Because once you've done that, you can start reading things off. So already we've got all the asymptotes, we've got their nature. Now again, positive, 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 minus 12, so it's going to start in the negative region. Where are our crossover points, or our change of signs? Well, now I've got a quadratic on the top. And the first changeover is going to happen at minus 1. Or one of them will. And the other one's going to happen at plus 2. Okay. Remember, I said our first part of the graph is here, and there's no changeover in here, so let's draw it. There it is. Normal asymptotes, so we're going to have the next part here. Now we would expect it to come up here, but because we have a changeover, it's going to go through and down. I didn't bother looking for a y-intercept because the y-axis is an asymptote, so there'll be no value on it. We have a double asymptote here, so we're going to have a corresponding part of the graph here. And we would normally expect it to loop like this, but we've got another crossover point. So it's going to come up and through and do that. And we've got another double asymptote, so it's going to be matched by the graph on this side, which will come down and be asymptotic to the x-axis. So with two crossover points, we've got two of these squiggles in the middle. And again, I suspect this comes much lower and goes through, but these points are guaranteed. That's what these tell us. So that's that top one. Let's tick it off. Let's look at this one. Last one for the video. Okay. Last one to go. Horizontal asymptote, as we've already agreed. Vertical asymptote at -1. And this term cannot be factorised. Now it's going to cause us a little bit of problem, and I must admit I haven't looked this up, but we'll talk about that in a moment. You might recall that when we graphed it alone, we got graphs like this, that were asymptotic at each end but had a bulge. And when that's in the denominator, something else happens, and we'll talk about that. Positive, 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 so we expect our graph to start out here. But our changeover is going to happen when x is 2. So something's going to happen there. So I think you can work out already that the graph is going to be asymptotic here and dive down through 2 and go down this asymptote. Now, near 0, or for small values of x, this will have an effect. It will cause a bit of a squiggle. I didn't check the y-intercept, by the way. Let's put x equals 0 in, and we get minus 2 over 4 is minus a half. My goodness. Let's revise this. I think this will be coming up and just diving through really gently and coming down. Now, it could be there's a little bit of an S-bend or a little bump as it goes down here, thanks to this expression, this little term here. And to find out what's exactly happening, you would probably have to substitute some values. Of course, simple asymptotes, so the rest of it is relatively straightforward. But just be aware there can be a little bit of a kink in this relatively smooth curve thanks to this. I would encourage you to go and look at it on Wolfram Alpha. I will be doing so after this video. But basically, That's the shape of the curve. I really haven't done the asymptote out here very well, have I? So that would come down and be asymptotic to the x-axis. Okay, enough said. It's been a long video. I've tried to cover, what have I done, about at least 10 equations and 10 graphs, trying to explain the principles of how all the graphing of asymptotes, changeovers, positive, negative constants, etc., all have their part to play in good graphing of rational equations, rational functions. If you've enjoyed it, please leave a comment or like the video. Please subscribe, and I look forward to seeing you in the next one where we look at type 2 graphs, which should be a little bit easier now that we've done all this. Thank you.